Hi everyone, welcome back. This is lecture 3.9, and in this video I'm going to go over the first 4 sections of chapter 22, where we will be learning about the chemistry that happens at the alpha position of the carbonyl. So some of the topics we will talk about are the keto-enol tautomerization reaction, and we will learn about how the enols that are formed in that react at the alpha position as nucleophiles. We'll see how that's applied to a few different example reactions, namely the alpha halogenation reactions of aldehydes, ketones, and carboxylic acids. So with that, let's get started. So to get started learning about the chemistry of the alpha carbon and the alpha hydrogen of a carbonyl system, we need to learn about a fundamental process that occurs with all aldehydes and all ketones and carboxylic acids and esters, actually any carbonyl system that has an alpha hydrogen on it. Any carbonyl system that has an alpha hydrogen on it undergoes a phenomenon known as tautomerization. And what this is an isomerization. It's the process of changing from one isomer to another. And these isomers we designate with a name called the keto and the enol form, or the keto and the enol isomers. And we're going to look at how that process happens. But first, let's see what a keto and an enol form look like. So the standard way we draw a carbonyl with the C double bond oxygen is what we call the keto form because of ketones. Now, there is an isomer that we could draw, and that forms when you have the keto form undergoing an isomerization that we call tautomerization. And this is called the enol form. And it's called an enol because we have a protonated alcohol, except it's not a standard alcohol where we have 2 R groups on either side that are sp3. We actually have at that alpha carbon an sp2, so there's a C double bond to another carbon there, and that makes it an enol. So that's called the enol form. And it's really that process of that alpha hydrogen either being at the OH or being at the carbon. We call that the tautomerization. Now that H that I've circled is actually, it's not like directly transferred from the alpha to the oxygen. There's a proton exchange with the environment. So those aren't identical atoms, but nonetheless, it's a net transfer of that hydrogen to the oxygen. So what's required for this tautomerization is you must have an alpha hydrogen, and it appears to have migrated. Without an alpha hydrogen, this doesn't happen. Another feature of this is that the enol form is a minor component of any mixture you have with an enolizable carbonyl system. It's a very small quantity. It can be enhanced by addition of acids and different conditions, which we're going to learn about. But the enol form, just for now, it's a very small component of the mixture. So let's take a look at a few example molecules. And I've written down some names of some molecules. And what I want you to do is draw the keto and the enol forms for each one. So it's a good practice for nomenclature. It's also good practice for getting used to drawing enols from from the carbonyl systems of which they derive. So let's start off with 3-pentanone. So draw the 3-pentanone molecule and then try to draw the enol form for it. So as you can see, I started by drawing the 5 carbons for pentanone and putting the ketone on the 3rd position. And then to draw the enol, identify the alpha carbon, of which on this molecule there are 2, because of the symmetry, there are 2 identical alpha positions. So it doesn't matter which one I choose to draw the enol from or to. I just draw that double bond to one of them, and I get an equivalent structure. So that's my enol. Let's try another example. Let's do a cyclic one with cyclopentanone. So really the same thing here. I have a 5-membered ring with the ketone, and the enol form is just the C double bond C to one of the alpha carbons, and then I have the hydroxy group up there. So let's try another example. Let's try an aldehyde this time. So butyraldehyde, give that a shot. Now, the key thing to realize with butyraldehyde is, well, it's an aldehyde, and that means we need to make sure we're not moving that aldehyde hydrogen, but we're actually making the enol between the alpha carbon. So pinpoint the alpha carbon and make your enol to there. So let's do another example. Let's look at methylpropionate, an ester. So drawing methylpropionate, I realize I have a methyl ester with 3 carbon atoms on the acyl group. So I draw my methyl ester first, and then I attach the propyl group. Next, I identify the alpha carbon, and now I draw the enol with the carbon-carbon double bond between the carbonyl carbon and the alpha carbon. So let's try one last example, propionic acid. So similarly, I identify the alpha carbon and draw my enol to that. All right, so now that we've had some chance to see what enols are, let's take a look at how they form and the reactions that they undergo. So the mechanism of tautomerization can occur through both an acid or a base catalyzed mechanism. And I'm going to show you both. So as you can see here, I've drawn a generic carbonyl system with alpha hydrogens present. I've also drawn an acid, and therefore I'm going to show you the acid catalyzed mechanism for tautomerization. So the first step in the mechanism is protonation of the carbonyl oxygen by the acid. This forms the activated carbonyl species, and in the next step, an alpha proton is lost to generate the enol. Notice that it's an acid-catalyzed mechanism, and the acid that is used is regenerated. Let's take a look at the base-catalyzed mechanism for tautomerization. In the first step of the mechanism that's base-catalyzed, the base deprotonates the slightly acidic alpha proton. That pushes the electrons up to the oxygen to make a negatively charged species that we call an enolate. An enolate is like a deprotonated enol. So we have this negative charge on the oxygen, and what happens is that oxygen, being basic, will deprotonate the water that was formed from that deprotonation. Now, of course, that acid water could also be a different conjugate acid, depending on what base was used to catalyze this. I'm just using water as an example. But nonetheless, this leads us to our enol, and it regenerates the base hydroxide as well. So we can see that it's base catalyzed. All right, so now that we've had a chance to understand how enols are formed, let's take a look at their reactivity as nucleophiles and see what kinds of reactions we can do with them. So it turns out that enols are excellent alpha carbon nucleophiles, meaning they're nucleophilic at that alpha carbon position. So we can understand this if we take a look at an enol and its resonance form and draw a resonance hybrid of it. So as I'm showing, we can delocalize the electrons from that enol oxygen down to make a pi bond and then push the electrons of that ene to the carbon at the alpha position. This shows a resonance form where electron density is at least partially localized at that alpha carbon. And as an overall resonance hybrid, we see that we have an alpha with a delta negative and a carbon with a delta positive. That means we have a good carbon nucleophile. And we can use that carbon nucleophile, as we see, to do substitution reactions, and later we'll see we can use that to make carbon-carbon bonds. This alpha nucleophilicity is best demonstrated through a reaction known as the alpha substitution reaction. Here's a general reaction scheme for the alpha substitution. We start with our enolizable carbonyl system. This can be a ketone or an aldehyde, and in the presence of an electrophile, and we'll see the types of electrophiles we can use in this are varied, we can substitute one of the alpha hydrogen atoms with the electrophile. That's known as the alpha substitution reaction. We will see a number of examples of this. We'll see examples of aldehydes and ketones being halogenated with chlorine, bromine, iodine, and also we'll see the alpha bromination of carboxylic acids, also known as the HVZ reaction. Here's a general mechanism which explains, basic terms, the chemistry of all of those. Essentially, the carbonyl system undergoes an enolization, so it forms an enol. We've already seen the mechanism by which a carbonyl can form an enol, and that enol acts as a nucleophile, where the electrons of the enol make a covalent bond with the electrophile. This leads to an alpha carbon that is now covalently bonded to that E. But it also has this hydrogen on the oxygen atom. And through loss of a proton, we arrive at the alpha substituted product. Now let's go to the next page and see our first example of this reaction at work, the alpha halogenation of aldehydes and ketones. The first alpha substitution reaction of carbonyls that we will look at is the alpha halogenation of aldehydes and ketones. And here's the general setup for this reaction. We start with an aldehyde or a ketone. Now, with these conditions, we need to use an aldehyde or a ketone. We can't use an ester or a carboxylic acid. I will show you reactions that do allow those, but not this one. To the carbonyl, we add the elemental form of the halogen, so chlorine, Cl2, bromine, Br2, and iodine, I2. Typically, you'll see this most commonly done with bromine because of the enormous toxicity and difficult handling of chlorine, whereas bromine still just as toxic, just a lot easier to handle. And then iodine substrates that it produces in this reaction are very unstable. So bromine is a good sweet spot for this reaction. The product of the reaction is the alpha halogenated carbonyl. So we have a chlorine or a bromine or an iodine now attached at the alpha position. So we've done a net substitution. One of the hydrogen atoms has been replaced with a halogen. Let's look at some examples of this. So in this first example, I'm taking cyclohexanone and treating it with bromine in the presence of acetic acid. Those are the typical conditions for this reaction. Acetic acid providing the acid to enolize, and we get alpha bromination in that case. So in the second example, I'm showing an aldehyde instead of a ketone. Same conditions, we're using bromine and acetic acid, so we expect to see alpha bromination of the aldehyde. Now in this example, I'm showing a methyl ketone with an aromatic ring on one side. And it's important to realize that because of the aromatic ring, there's no alpha proton on that side. The only alpha protons that exist are at the methyl group. So we will be substituting one of those methyl hydrogen atoms with a bromine atom. The examples I've just shown you all only have one possible enolizable alpha position. Now, what happens when we have a substrate that has two different alpha positions? Well, it turns out that we see there is a regioselectivity, a preference for one of the different alpha positions to be halogenated. Let's take a look and try to see if we can figure out why that is. So in this first example, you can see that I have a unsymmetrical substituted ketone. So I have a methyl on one side and just two hydrogen atoms on the other. So we have two different alpha positions, like an alpha 1 and an alpha 2. And the question is well, which one would be halogenated? So let's see what the result is. So as you can see from the results of this experiment, and I can tell you several others, that it turns out that the halogen goes to the more substituted side when there are two different alpha positions of differing substitution. And a really good question to ask is, well, why is that? So let's take a look at the enol intermediates that form during the mechanism. So the first thing we should do is correlate each of these enols that I have drawn with which alpha position they originate from. So we can see the first enol originates from enolization of alpha 1. The second enol, therefore, originates from the enolization of alpha 2. Now we need to correlate each of the enols with each of the products. So looking at alpha 1, we see that it correlates with the major product. And looking at alpha 2, we see that it correlates with the minor product. So why is it that alpha 1 leads to the major product and alpha 2 leads to the minor product? Well, if we compare each of the enols that we have here with what we know about the stability of alkenes, we should be able to say that a more substituted alkene is more stable. And likewise, a more substituted enol should be more stable than a less substituted one, which we see with alpha 1 and alpha 2. So alpha 1 is more stable than alpha 2. Now let's take a look at the mechanism for this alpha substitution in detail. In the first step of the mechanism, the acetic acid provides a proton to the carbonyl oxygen. The conjugate base of acetic acid, acetate, is able to deprotonate the alpha position of that carbonyl that's been activated. This is what generates the enol. The nucleophilic enol attacks the bromine molecule, thus making a covalent bond at the alpha position to a bromine atom. Now, in the last step of the mechanism, we have to lose that proton on the oxonium. This is where a bromide or another acetate molecule can deprotonate that oxonium, and we are left with our alpha halogenated aldehyde or ketone. Now, there are some interesting applications of this alpha technique, as well as some interesting insights into how the reaction works on the next page. Let's take a look. Now, you might remember I mentioned that the enol is a very short-lived and very low population species in terms of compared to the carbonyl. So how do we know the mechanism proceeds through an enol? Well, an experiment I'm showing here with deuterium oxide, D2O, with the same conditions like with acetic acid, leads to deuteration at the alpha position. Now, that implies that an enol is formed because it gets protonated by a nucleophilic alpha carbon, because deuterium is basically a hydrogen atom. This is also a useful method for radiolabeling an alpha carbon. Another way that this reaction is used is to prepare alpha-beta unsaturated carbonyl compounds. So for example, cyclohexanone can be converted into the alpha-beta unsaturated cyclohexanone by using this technique whereby on the first step we alpha halogenate, say with bromine and acetic acid. Now that bromine is a good leaving group, and we can do an elimination reaction, an E2 style elimination reaction by using a base. And it turns out pyridine is good for this task. We warm the molecule up with pyridine, and we get an E2 style elimination, as I'm showing here in this mechanism. It's also possible to alpha brominate carboxylic acids and esters, or type 2 carbonyl systems. Now, this doesn't work on amides, but it does, or acid chlorides for that matter, but it does work on carboxylic acids and esters. And the reaction works like this. You take a carboxylic acid or an ester, and you treat it in the first step with PBr3. What that does is it converts the carboxylic acid into an acyl bromide. In the second step, you treat it with bromine and water, and you form an alpha brominated carboxylic acid. The mechanism involves enolization of that acyl bromide. So the acyl bromide, I'll draw that for you here, just has a bromine where the hydroxide is. Now, it's this acyl bromide in the presence of HBr, which is generating during that phosphorus tribromide reaction. This causes the enolization. That nucleophilic enol is what attacks the bromine and alpha brominates. It's here where the water that's added in the second step, attacks the carbonyl carbon in a nucleophilic acyl substitution reaction, displacing the bromide and forming the carboxylic acid. Now, this is known as the Hell-Volhart-Zielinski reaction. So here's an interesting mechanistic alternative for the Hell-Volhart-Zielinski reaction. So we start with a carboxylic acid. However, we have a hydroxy group at the terminal carbon. Now we treat this with the Hell-Volhart-Zielinski conditions, namely phosphorus tribromide and bromine. However, notice no water is added. Nonetheless, an ester is formed with the alpha bromo attached. Propose a mechanism for how this might be produced. So I've drawn the intermediates I would expect thus far. I convert the carboxylic acid into an acyl bromide, and then that enolizes. And then we see the nucleophilic attack onto the bromine, like we would expect. This creates the alpha bromo carbonyl. And now, instead of having water convert into a carboxylic acid, we get an intramolecular attack of that hydroxy group in an acyl substitution reaction. This generates a cyclic ester, or a lactone, with an alpha bromo attached. A final step would be deprotonation, probably by the bromide, to leave us with the neutral lactone with that alpha bromo attached. So that's a decent mechanism, I think, for this variant of the Helmholtz-Zielinski reaction. And that will conclude our lecture. Let me know if you have any questions. I'll see you next time.